late August.
Oh, okay. So
Just started.
just started. Okay. All right. I think we have who we are going to have today. So, catch everybody up to speed on why we decided to do this. Because there's, well, there's a lot of us modeling and building, and of course I'm departing soon. So I thought it would be useful to kind of get you up to speed on where we've been as far as modeling goes here and where we need to go. And so this first meeting kind of is just more of what is MODFLOW and kind of an overview. But then what I'd like successive meetings to go through each of the sort of the packages or the elements of MODFLOW and have more of a discussion on where we're at and where we need to go. I was just looking at Vlad's graph and thinking, you know, in some respects, I have it really easy. But now going forward, we have a lot more data. And we have a lot of transducer data, and that's going to make everything from a modeling point of view much more interesting, but it's also going to make it harder because the more data you have, the harder something is to model to. So models are really easy in simple systems without a lot of data. And so that's where, you know, most of your examples are from. We're especially challenged in Illinois versus Texas or wherever because the glacial system is just a mess. So our models, say, of Northeast Illinois and the bedrock system are, until it got all mucked up with cross-connecting wells, was fairly simple. And so, and actually the simple models worked better than the more complicated models. And I can get into that until we get enough of the complication in there that the complicated models actually work. So the reason we model, I mean, there's a lot of reasons we model. We have some specific question we want to ask, but I mean, the main reason I see modeling is it puts all the data together. So everything kind of has to add up. So if you look at the potentiometric surfaces of, we were just looking at for Lee Whiteside. Well, I look at that and go, oh boy, it's going to be impossible to model because we have high water levels over here and low over here. But how does the water get in over here to get those high water levels? And you know, I look at the gradient of the Sankote aquifer going down towards the Illinois River. That's a really, really steep gradient. That means there's a heck of a lot of flow, or we're just not conceptualizing it right.
I'll make the point that I cheated with the Illinois River. I just picked an average stage for it, so it's not actually varying with the season. I just did,
well, that's probably safe with the Illinois River because it's a series of lakes anyways. But yeah, no, not up there, I guess, or not even. Yeah, well, we get into that. But yeah, so the purpose of putting a model together is, I mean, there's the questions you want to ask. Is contaminant moving somewhere? Is this irrigation causing drawdown? All that kind of stuff. But the advantage of a model has is it sort of has to explain everything. And so that includes chemistry data, for example, isotope data, where you're using isotopes for modern carbon or something. So one of our Muhammad Aquifer studies made absolutely no sense because, wait a second, there's all this modern carbon in the aquifer. How did that get here? So it wasn't until the isotope work was done that the hydro work makes sense. And so, you know, because for the Muhammad Aquifer, for example, through central Illinois, gets very old, gets dead, except for one tritium hit, which made absolutely no sense, but we got that figured out. Then you have very dead carbon, and then it starts to get younger and younger as you get recharge coming in with modern water. So, you know, you have a lot of geochemists. No bad mouthing geochemists here, but you know, they'll look at the geochemistry and go, oh, well, okay, there must be a source of water here because the chemistry changed, you know, and you see that a lot, but you don't see any mass balance attached to the water flow to see if it makes any sense. I'll pass around a paper that I just came across, cleaning up. It talks about why the driftless area in Illinois wasn't covered by glaciers, and they're assuming all the meltwater as the glacier came got channeled through karst features and never, so the glaciers couldn't go up over the driftless area because all the meltwater was being drained away. So is the permeability of the bedrock high enough to support that? You know, it's an open question, you know, but that's something you put a model together and say, okay, there's this great glacial theory, but this doesn't make any sense. And so, and even on a small scale, I've done a lot of work with Building 5, our surface water people. No offense against surface water people. Mike used to work in Building 5, so I'll try to refrain from any nasty comments. With Bill Bogner, we did some budget studies of a lake in Chicago, and so naturally I couldn't explain some things, so I blamed it on surface water, and he couldn't explain some things, so he blamed it on groundwater. And there were, had we done our independent studies, or our studies independently and gone on, I would have wrote my groundwater report and said, okay, so much groundwater is discharged in the surface water, and go on. And then Bill would have written his report and said, well, groundwater contributing this and causing this, and they would have moved on until somebody read both reports and said, well, this doesn't make a bit of sense, you know. And so, and there's numerous examples of that. And so we need to talk a lot about groundwater and surface water. And it is a primary driver for a lot of what we do in groundwater. And I drew kind of a classic example up here. Sorry, this isn't on PowerPoint. But say we have a stream and a groundwater table, and we have recharge coming in, we have some permeability, you know, and we've got Darcy's law controlling the amount of flow through that aquifer. So this could be the Green River lowlands and recharge and stuff. You could make a model work using a whole variety of R's and K's to get this same profile. So if you increase the K, you increase the recharge, and you can probably match your monitoring well data pretty well. Or likewise, if you decrease K, that's going to prop up heads. So you're going to have to decrease R. So you have this relationship of R and K where you could have a couple of models where you have what I call a wet model or a dry model. So a high K and a high recharge, or low K and a low recharge. Two vastly different answers. And that is kind of what's referred to as non-uniqueness, or the non-uniqueness of groundwater flow models. So the only way to sort that out is your Q value and what you're discharging to a river. So you can, you know, make fairly good guess of hydraulic conductivity, but hydraulic conductivity is something that varies by orders of magnitude. Even sands in Illinois, in our models, we have values from say 30 to, well, in the case of Carpentersville, 4,000, which is a whole other special case. But the Bahamas sands around 275 feet per day. I talk in terms of feet per day, but so that gets us back to looking at the streams. You know, and that's a real problem if we have, maybe the Green River is almost too big, the Rock is definitely too big to really get a handle on how much groundwater is coming out. Now, smaller streams, you know, the Q7 or low flow streams, we can get good numbers on, or we can figure out, okay, our low flow is 2 CFS in this stream, so I can't have a groundwater model that's pumping out, you know, 20 CFS, because that water is just not there. That's a simple answer. And so that's kind of where I'm leaving off and you guys are picking up, because as I look at it, you know, the models we've done are steady state. So they're you know, a snapshot, you know, we don't have things changing, or if they are changing, we're changing pumpage on a yearly basis. So a yearly time step is really a series of steady states. It's not a true transient. And we'll talk about that when we get there. And so if you assume, you know, groundwater is at steady state flow, and it's a lot more steady than surface water, you know, if the gradient changes substantially, do you get, you know, significantly more groundwater that you could get 20 CFS out in a rainy period if the groundwater jumps up 2 feet? Because what we don't do a good job in is, say this is the gradient and it's 0.001 or something, 0.1, you know, and then we get rainfall coming in, you know, and everything pops up. Well, now what does this gradient suddenly become? You know, it could become something that's, and this is exaggerated because the natural gradient is probably a lot flatter, you know, but suddenly this could become 0.0004, at least locally. And so suddenly you're driving a lot of groundwater locally, and now back out away. Maybe not so much. Illinois is all drain tile. So that's going to really muck things up. And we'll talk a lot about drainage and how to do that. So going forward, getting this Q value is going to be a lot more important, because that's, again, what makes this problem, puts our dot here on this plot where it needs to be. But I might refer to a model being wet or dry. So having a wet model is a lot easier to do. It just solves a lot of problems, and you never have wells going dry. You never, you know, everything's hunky-dory. You don't get a lot of drawdown when you should have drawdown. And a dry model is a lot more difficult. Now, I'll say right off, because we try to calibrate our models to low flow. So the Q710, or what the low flow is in the river. So, so I would say our models are dry, but I call it dry, or they're on the drier side. When in reality, we're probably moving up and down this plot, or maybe not the K, we'll be moving up and down. The K is not going to change, but so anyway, so things are going to get more difficult going forward, is what I want to say. But I want to show you guys where we've been and why we do what we do, and maybe the errors of our ways, or as computational, what do we want to call it? It's gotten more efficient, and our computational power is increased, we can do a lot more.
So if you're falling above that trend line, that's a wet model.
Well,
Not
no.
Anything to do with it.
So these are different model runs where we can have low recharge and lower K versus high recharge and higher K
I see.
to get the same
Yeah.
match at our observation wells.
I see.
So a wet model would be high K and high recharge.
Yes.
Yes. Gotcha.
So where this all gets mucked up is in stressed aquifers like the Cambrian Ordovician or Champaign or Green River lowlands, where we have two different stresses. We have the non-pumping stress and the heavily pumped stress. And so the no matter, things are going to fall out because you'll need to match, not only the steady value, but you also need to match a cone of depression. And so that's going to give a lot more control to your K than you had before. But we are really, really lucky from a modeling standpoint in Illinois to have big cones of depression, because you have to model it without the cone of depression and with the cone of depression. And a lot of cases you see are an aquifer is unused and someone's going to come in and heavily use it and say, what's the impact? Well, you don't really know, because you don't have this other stress to calibrate to. So, we have a lot greater confidence in our models that have big cones of depression because they have different cases to go through. So let me go through some of the slides here. This is some visual mod flow, I guess, but one nice thing about models, you make a lot of pretty pictures, so if nothing else, you can make yourself look intelligent by having, all kinds of surfaces and stuff. I don't have some videos on here, but I had some videos here that was on a little Discovery Channel thing once, and you can make all kinds of good stuff. So behind us, this is a picture from 1964, and we can play with this later, but this is how the Water Survey started to do modeling, the analog models. So, Darcy's law is very similar to
Mm-hmm.
Yeah. So this is current versus flux, and voltage versus potential, and hydraulic conductivity is similar to resistance. Their electrical resistance is inverted. But other than that, so electrical theory follows the same theory as groundwater flow. And so a lot of Darcy's law and a lot of groundwater equations were all stolen from heat flow, which is also very simple. So you can look through a heat flow paper and understand it if you understand groundwater flow. I don't recommend it because they don't make that much stuff. But and so this is how they did it early on. And so they soldered all these resistors. So the resistors are acting as the hydraulic conductivity, the K. And then this power supply puts a voltage across the thing, and then the current is flowing across it. And then these are wells that are pulling out, I guess, electricity. And you can turn them up and down, and it's pulls more current. So then you'll get a drawdown. So you can put your voltmeter between two spots and get or between the boundary and different spots, and you get different voltage readings, which you then can convert back to head. And we can play with it. later. I'll show you how to play with it, and I would suggest just playing with it yourself. You can't electrocute yourself too badly, so. If you go to the Illinois room in the other building, you'll see the one for the Muhammad Akbar in Champaign. So this is Farmer City on the topo sheet here. So Champaign is in here. There's actually a whole series of nested ones. This is actually 2 layers. Not 2 layers right here, but in some areas it becomes 2 layers. You can see it gets darker right here. There's another row of resistors below that. And there's also capacitors. What do capacitors do? They store electricity. So this is how they did storage. So this was a transient model. So a transient model, you need to account for storage and go from there. So actually down in the war room, there's a paper sitting out. I think it's sitting out on how these work, if you're interested. We then went to the punch cards. I am not old enough to have ever used punch cards, but just barely missed it. Darn. No. And so Bulletin 55 is written by Tom Prickett. He was here for a while, very famous modeler. And then he kind of stayed around and tutored us a lot after he formed his own consulting firm because he was doing so much work on the side when he was here. Did that for 20 years and then retired and just did expert witnessing. But then in his later years, unfortunately, he died young, came back and would like to come in and shoot shit and pick apart my models and what I was doing wrong. And most of it actually revolved around storage. But it's used punch cards and a small anecdote. Supposedly, according to water survey lore, you know how true that is. No, to our computer guys who were around at the time, this was the first off-site job, at least non-military job, of a computer program. So Tom was taking these stacks of cards, because each card has a line of code on it, down from the water survey, which is now CAB at the corner of 6th and Springfield, down to DCL, and feeding it through the card reader and running the program. And I thought, oh, well, that is not very convenient, to take things down on a dolly, because it was a big thing. It'd take all night to run, but runs like that now. So they hooked a phone reader up at the water survey and had the cards read over the phone line they set up a special phone line, I should say. This is all brand new technology. And so we say it's the first internet job, remote internet job. But it was in the early halcyon days of computing at U of I. But I digress. And I put one of the cards up in the war room if you want to look at the cards. So I can say the simple code, actually the entire model is written in here. The whole code is in here. It's not very long. And that's 2 pages, I guess. But if you ignore all the comments, what's actually on the cards is really short. Most of this first page is just comments. So, and they were able to do this model of Northeast Illinois. So, it doesn't take a whole lot. Like in the early days, codes had to be extremely short because it took forever to run. And so there's extra copies of Bulletin 55 down in the war room if you want to read those. I saved every copy we have because it's kind of a revered document around here. Of course, having electronic code just opened up the world to, changing things versus if you change the resistor model, you need to get out your soldering gun and have at it. And so Tom Prickett actually had another wow moment with the internet. He was at a conference in 1973. It was 73, he told me. And they had come out with those modems that you stick the handset of the phone into. You might have seen them in an old movie.
Mm-hmm.
But he actually ran one of his models at a conference. He had that much faith that it would work.
Wow.
And that he was giving a talk, I think it was in Denver, and he actually phoned back here to Champaign and ran his model live in front of an audience. And they're like, whoa. Yeah, so, you know, since these days, things have just gotten bigger and bigger and more complicated and more complicated. It's Fortran, by the way, Vlad, if you don't understand it.
I know.
You know, if you need a little help with Fortran, I'd be happy to help you. So there's a couple different codes that came out. And then the USGS came along with more time and money and came up with MODFLOW. So this is a much thicker document. And the code actually came out in the early 80s, but they didn't write the manual until 1988. So most people had figured out how to use it without the manual, or in rough drafts of the manual. Typical USGS. You know how long USGS review takes, right, Dan? Forever, yeah. So, so we'll talk about that in a minute. These are just some more, some of the newer packages now. Instead of punch cards, they have what we call pre and post processors or GUI interfaces, and make all the pretty pictures or get the data in. So we use Groundwater Vistas. We used to use Visual MODFLOW, but I think we have to keep our eyes open and, you know, change as things change or as they get better or not better. So we're kind of wedded to Groundwater Vistas right now, but I think that's something we need to be very wary of, because it's, you know, a one-man operation, and if he gets run over by a bus, then we're stuck, you know. So
He retires.
or retires, yeah, he's older than I am. And his brother is, I don't know, some hermit in the mountains of Pennsylvania that actually does the coding. So
Really? I didn't know that.
yeah, Doug, yeah.
You never see Doug.
You never see Doug,
It's
yeah.
always Jim.
The mythical Doug, yeah. But anyways, so, you know, there are other programs out there, so one of the other things, of course, is contaminant transport has been added to MODFLOW, so you can make all sorts of pretty pictures of plumes and, you know, the tetramethyl death going to a specific house or whatever, wherever it's going to go. Yeah, and so, you know, kind of neat cutaways and different things you can do. These are, you know, good for public meetings and things like that, or at least it makes it look like, you know, what you're doing. Oh, well, it's hard to argue with that because it looks scientific. And so there's many different ways to modeling. This is another way, and we'll talk about gridding, you know, different approaches, and well, when we talk about gridding, we'll get to this, but this is kind of a different way where you'd like break everything up into even blocks versus, you know, layers versus this and that, following the geology. So this is a fault zone model. So here's some of our models now. So the one on the top here is a Mahomet model. So we have layers represented with thicknesses and elevations, and can display that all graphically, you know, with different colors for the different stuff and so on and so forth. Some of Devin's magic from Kendall Chicago is here with all of the multi-aquifer wells are in the lower ones. So I think we'll leave this discussion to when Daniel's here. Oh, Daniel decided to show up. Oh, perfect timing.
Okay.
No. I was just, yeah, explaining why we model and then some of the past models, plasm and stuff. And up here is the kind of our old model versus the new Illinois groundwater flow model. Maybe I take off the word new. I don't know. Nah, I'll leave it in there.
Yeah, leave it in there. It's always new. It's always evolving.
It's always evolving. Yeah. So, computing power is greatly increased, but it's not just that. It's our tolerance for long run times. No. And, getting the data in and having the data in order to put into the model, of course, is a big thing. So, each of you are kind of working on different things as far as data or the pumpage data or the river data or whatever, or a specific region, Green River Lowlands or whatever. Dan's working on the transmissivity and that sort of thing. So all those pieces come together, and we're doing that all on a much better resolution scale-wise. And so this is just kind of to show the difference between where we were and where we're going. So you can see in order to run, this is originally based on Joliet, and so there's finer resolution here, and then of course it got really coarse with really odd shaped cells as you went away from that. But what we found is, okay, yeah, we want to model a Muhammad down here, and we want to model Green River Lowlands, we want to model Middle Illinois and King County and this and that and the next thing. And these models didn't talk to each other. They weren't based on the same grid, or they weren't based on the same underlying data even. And so that's the direction we're going, and we can kind of save that discussion more technical as we go along. So what's the beauty of a groundwater flow model? Is that it basically is a mass balance. So it solves Darcy's law with mass balance is kind of the way I say it, or law of conservation. So you're combining Darcy's law and mass balance. So just like with that analog model, you're putting voltage across that thing, and that voltage has to go somewhere. So it's sort of a perfect model because there's no math errors in it. It's flowing, unless you're generating heat or have a short, then you have a mass balance error. But it's dividing a model is dividing the aquifer up into a cell, and it's keeping track of how much water is flowing in and flowing out. So you've probably all seen the groundwater flow equation. This is the standard form with the K value that's allowed to vary in both direction and space. So anisotropic and heterogeneous, and then it's simplified from there. In modeling, we usually have our KX and our KY the same, unless we're trying to do fracture flows or something. Our KZs, we change quite a bit. And our KZs are really more important on the confining layers. So we have aquifers and then confining layers, and if they're sand and till, there's 7 orders of magnitude. So or even sandstone and clays or shales. So what really is important is the KX of the aquifers and the KZs of the confining layers. You'll find that the other parameters are largely insensitive. those are kind of the driving parameters. And so,
Do you normally assume that, oh, I'm sorry, I didn't want to interrupt.
No,
Do you
go ahead.
normally assume that KX equals KY?
yes.
Okay.
We don't have a lot of evidence to say otherwise. And you know, if we were modeling a fracture network, that might be one case where you have dominant fractures going one way. If you're on a very small scale, you know, where you're in one river valley, you know the sand all was deposited one direction, yeah, you might, but our glacial geology is kind of too messy to really have any confidence in that. We do have one study site out in Mason County where we have basically 100 wells in the network. I don't think they varied KX and KY in that. I'll have to check. So, you know, you look at any textbook and you'll get this equation for groundwater flow. So you're solving this for head over time. Of course, that's a storage term because you can take water out over time. What the models do is also add this W term. So that's flow, this extra flow in and out of a cell. So that can be a well or something else. It's not, you know, something that's added to the flow system. In addition, because with this equation, basically you only have boundary, or you only have flow without any boundary conditions. There's nothing to change anything. So, you know, so the model has this W term, which could be recharge, well withdrawal, could be a river interaction. It could be anything. So how does the kind of a model work or solve? So just pretend this test case is an aquifer, and we have a confining layer and this confined aquifer down here. We have a fault, which in this example is a constant head, or it's holding water levels high. There's a river or something, and water, the head over here is going to remain constant. Then you put in this line of wells and you draw the water level down. So over time, you turn on these wells and you get the head to drop over time. And so eventually you'll reach, you have basically two conditions. You basically reach a steady, a linear line is basically your water table when you reach steady state. So over time, you know, your head change becomes nothing. So the model also basically solves it the same way. So if you have a steady state model and you hit run, it's not looking at the model in respect to time or days, but it has to solve for the new heads, right? So you're adding this condition in, and your model might start off with initial heads that are all flat, and then you start your model and you say, oh, it has all this Q in it, so it starts pulling water out. So the model, when it's iterating, even in you know, in steady state, it's going through this same process. So the first time it iterates through, it says, oh, I need to take all the water out of this cell. So the head drops, you know, but the head remains steady out here. And then so this might be what the result is after the first iteration. So this might be after the second iteration, the third iteration. So you have to let the model run long enough that it iterates through all this so you actually approach, you know, the solution you want. So instead of this being time, you can think of this as number of iterations. And so, and this bottom line here would be a convergence criteria. So we want to keep running this model until our heads stop changing. And you can get very different answers on if you use 1 or 0.01. You know, there's models that aren't basically run long enough. It's one of the many ways you can cheat and hide errors just to have a high convergence rate. So I should say, like, when I review a model, there's many things I look for, and there's kind of a list of ways that people cheat, or they don't necessarily realize they're cheating, but ways to make model work. One is to have a very wet model and no you know, kind of surface conditions. Another one is to have a very high convergence criteria. But so we'll probably spend a whole lecture talking about solvers.
Sure.
And I got my whole visual MODFLOW fired up so I could show in real time what the solver
So
is.
an actual good solver
Yeah.
depiction.
Yeah.
Yeah.
So that's just a preview of a lecture on solvers, because there's a lot that goes into that.
Mhm.
So this is your, let's say, a 2D model domain. It has rows and columns. MODFLOW starts with rows at the top and works down. Most software works at the bottom and goes up, and so there's all sorts of confusion there. But generally, columns increase left to right, so that's good. So oftentimes you see things that are inverted, and you're kind of scratching your head. Not that that's happened to Daniel anytime.
So just about every time I try to code it.
Yeah. Yeah. Fortunately, Python counts backwards pretty well. Yeah. So again, we're looking at this flow equation that we're trying to solve. So when we're trying to solve this, it's going to be looking at the head that's in the cell and the values of the cells all around, because if something is going on in this cell, it's going to affect these other cells, right? So, so to go through and solve this equation, so we're basically solving Darcy's law over each of these faces of a model cell. And it's just, and then in 3 dimensions, of course, we have the top and bottom as well. But when we get over to the edge, it doesn't know what to do, because it's going to look, well, something is going on over here. If you write the math the way you're supposed to, you know, it's doing this 5-point operator for each one, but then it's got to do something about the boundary. So the boundary can be no flow. Say, okay, well, there's nothing going across here, it falls out of the calculation, 0, or it's a constant head, and the head's going to stay the same. So we're always going to be calculating a new Darcy's law of flux across there. So when you're, you know, modeling anything, the boundary conditions kind of control everything. So without any boundary conditions, a model won't solve. It has nothing to, what I say, call hang its hat on. So if you just tried to solve this by itself with no flows, no river conditions, no nothing, it doesn't know what to adjust to. So just like keep working its way down to 0 or just not go anywhere. So you need some kind of condition that tells you what a head value is. So it could be a river, it could be, you know, something that says, okay, head here is 600 feet. Then, now I have something that I can, you know, resolve to. Yeah, so again, here's this 5-point operator. You use the head you have in a cell at your current iteration or your previous iteration, and then the heads all around you. And basically, through all the numerics, you come up with these coefficients, and then you know, and some things drop out and simplify, and then you have this 5-point operator that you're using to solve for flow.
So SIP there is the solver, correct?
Yes,
Strongly implicit.
procedure.
There's a lot of solvers, but that's one of the
It's kind of the simple one of how.
simple.
Yeah. So again, to get more complicated in solvers, it just comes as a giant matrix equation that you're solving for. All the ones that are here are zeros. So when your computer's sitting there churning away and it's just thinking and thinking and thinking, and you're getting errors and other things, this is what it's solving. So, so for each cell in your model, it's going to go through and do this. So the more cells you have, the more time this takes, because the bigger and bigger this matrix gets. And then, yeah, we'll talk more about solvers. And so you'll see these are the coefficients. These are the head values at each node. And then these are all the boundary conditions, basically fall into there. Not quite, but. So we classify groundwater flow as transient or steady state. And this definition is nearly as hard as you think of it, or as certain as you think it is. So, for example, you know, we have a steady state model, the Muhammad Aquifer, just one time step, just solves and that's it. Or we have a transient model that says, okay, let's vary pumpage every year based on our IWIP data, our water use data. And it's technically a transient model, but it's really solving a series of steady states, because if you change pumpage in the Bahamut, the new heads will equilibrate in a day because it's so permeable. And so, so if you were to look at let's say, you know, if your pumpage is, you got to step up in pumpage here, and then you're looking at, this is time, and then if you're looking at the head, it's going to come along and say, there's a pumping change. It's going to drop like that, and then there's another one. Oh, okay, goes back. You know, it's rather instantaneous. If your time step is a year long, then your head changes are almost instantaneous. So a true transient would be more, you know, something like where your Q changes, you know, and you have all these different time steps in here, and you have enough time steps to kind of capture the changes that's occurring, and then you get, you know, something that might be more like this, you know, rather than this sharp, you know, everything looking like a Tice curve response. So going forward, that's what calibrating or trying to mimic, say, the transducer data from the Green River lowlands is going to get much, much harder. Because now, you know, your hydrograph might look like this, where you have a water level coming along and then it drops, then it drops some more, you know, and then it comes back up and then, you know, drops again. So, you know, unless you have a lot of transient time steps, you know, you're dividing the problem up, you're never going to catch that. All you're going to get is something that looks like this. You know, if you only have one irrigation season, you're only going to have one drawdown data. And this is probably going to be your average queue over the summer. So if most of the queue is occurring in a 2-week period, you're going to completely miss that. It's sort of like taking hand measurements. You know, if you calibrated your hand measurements, you're going to miss a lot of the action that's going on. So I started off by saying it's a lot easier for me because things are a lot simpler, because things are more steady state models,
Well, sure, as we
less
go
data.
from
Now we're
annual
going
average to seasonal down to daily, like we talked about in St. Louis, or monthly, like we're now doing in Joliet. what that pumpage is at that point in time becomes more and more important. What the river conditions are.
The modeling is going to get a lot
Yeah,
harder from that respect
yeah.
as we go forward.
But if you're wanting to do a full contaminant transport, what is the direction of this contaminant plume? How does it change when the river goes up versus down?
Yeah, I was reading a report on that yesterday and thinking about that same thing. A lot of these responses in river stage are very rapid, and so
Yeah.
you're going to get like the switches in the groundwater gradient are going to just, I mean, they're not going to last that way for an entire year. So that, like, we can't view it as this longer steady state trend.
Yeah, yeah.
Yeah. And kind of like what I said before, a steady state model, the model is going through and solving it, and it doesn't use time, but it's kind of solving it in the same, solving that initial steady state as a transient, because it doesn't have the right answer right away. It's got to iterate to find the answer. And so, unless it's new, no. So MODFLOW, that's what we're all about nowadays. And so it's kind of in the basic model written in lovely Fortran. Gladly, huge Fortran fan.
Sure.
And
He's gonna learn object-oriented Fortran for us.
good. So it's written by the USGS and, well, finished in the early 80s, I guess, and has been used since then. In the mod stands for modular. So there's the basic 5-point solver that I just showed you. I mean, that's not going to change. There's nothing about that equation that's going to change over time. But it's the boundary conditions and the things you add to or from, you know, and how you treat that W term. So, you know, this part isn't going to change. This is physics. This is set. But what MODFLOW allows you to do and improve over time with different newer versions of MODFLOW is the W term and how you get boundary conditions in and out of a model. You know, well, those don't really change, but, you know, there's different ways of solving this matrix and going about it. But I should mention that you get this big matrix, and this is not a word I can't say. I keep saying parallelizable, but
Sure.
it's hard to make this parallel. Or no one has successfully made it parallel. SAMG solver maybe.
SAMG.
Nothing that's been
that we've
easy.
gotten any advantage from.
Yeah, we've gotten any advantage of. So it's still this long linear problem. So you see a lot of, you know, so blue waters would do us no good because supercomputers work by breaking a problem down and parallelizing it, or paralyzing it. You know, and solving the problem really quickly. But, you know, getting a faster machine, well, a faster machine helps, but, and having more cores helps some of the in and out processing that has to go on, but basically it doesn't make the program run any faster in a meaningful way.
Yeah, we found one of the biggest advantages of going up to a Modus was being able to navigate the larger models with the GUI rather than the actual runtime of the model. The MODFLOW side didn't benefit as much as the graphical user interface that shows you MODFLOW.
Yeah. It's the speed of the chip.
Yeah.
That's everything. So if it's the same chip in this laptop versus Modus, it's going to run just as fast. Well, it's got to write a lot of files, and that's sped up by Modus. But yeah, so I just wanted to make that point. And there are other attempts we need to consider The Dutch have decided, well, okay, maybe I can geographically or divide the grid up into sectors and solve each of those sectors and marry them back. Maybe works.
Unless you could just attribute it to the Dutch.
The Dutch, yeah. The crazy Dutch. Yeah. Yeah. Well, we won't get off about Dutch. So, I mean, those are all things we need to consider going forward. Is there an advantage to some of those other solvers? So, MODFLOW, getting back to it, is the industry standard. Everyone's using it. It's, you know, what's under the hood of every GUI, so visual MODFLOW or Groundwater Vistas or GMS or any of these fancy programs out there, all run MODFLOW and all write almost the same exact files that are back here in the report that are read in by, oh, there's lots of examples in here, but, you know, it generates these text files that are read into that MODFLOW Fortran code. I don't think it's changed since 2005. Well,
What's that, the code?
yeah, the underneath, the very core of the code hasn't changed.
Is whenever they got into the core of the code started to change.
Yeah, some of them tried to introduce some black magic into it. Yeah. So it has these modules again for the geology, you know, so the surface layers. And actually, some of the original models didn't have surfaces; they were just transmissivities, or you know, there was uniform grids. But now there's a module to define the grid spacing, that sort of thing. Of course, there's modules for hydraulic connectivity and storage. You have to have arrays that show you what your hydraulic connectivity values are. So for each cell, it defines, or you have to define a hydraulic connectivity and a storativity for each cell. And then you have a variety of boundary conditions that you can use. So you have to have at least one. Otherwise, there's nothing to solve on. So those can be constant heads, where head is kept at a certain level. Say you want to model the Green River as a constant head, or the reservoir, the Rock River, because that doesn't change much. But there's a constant head. Lake Michigan is a nice, well, almost constant head. Fluctuates by 5 feet, so you can argue that. There's a constant head if you're modeling the sandstone. It's not a constant head if you're modeling the beach sands in Zion, Illinois, for example. Wells, of course, those are a constant flux. Recharge is a constant flux as well. You're dumping water on top of the model. And here's one of the greatest misconceptions of modeling. And we'll talk about recharge a lot. So here's your cell, you know. So you're calculating RC flow in and out. And there's a three-dimensional model. This is the land surface up here. I would represent land surface with pine tree. So your recharge is coming in here. Most people say, okay, so the recharge is coming in the top of the model and going somewhere, or going down. It's not what's happening. So there is a flow budget for this cell. So it's going back to, you know, the equation for the whole cell. And this water that's coming in, there's only one head value for the cell, right? So the water is calculating head at the center. So the water is actually, you can think of as coming into the center of the node, not the top. So the budget calculation and the head calculation are done at the center of the cell. So you think, okay, this cell is 50 feet thick. you know, I'm simulating a recharge, you know, getting through 25 feet of this before it, you know, gets into any calculation here, but that's false. The recharge is put in the model in the center of the cell. So what happens is the recharge passes through a lot easier than you think it does because it gets put in at the center. So if you were actually to divide this up into two cells, and you had two calculations here. So the recharge comes in this cell, and then it's got to work its way through this cell to get out. So you get a very different answer with two layers versus one layer in how this recharge is treated. So you have to think about that. You have to think, oh, this W term is putting it over the whole block of the cell, not just on the top. So I've seen many models that go awry that direction. Okay, we're going to be spending a lot of time about rivers. Rivers are a different kind of boundary condition where you set a head in a river cell, you know, whatever that elevation of the river is, you set a conductance or how, you know, the stream bed, whether it's clogged or very permeable, and then it takes water in or out of the model depending on the head in the surrounding cell. So it's called a head dependent flux. So if your head is changing in the surrounding cells, that river is going to take more water out. But so it can vary quite a bit, whereas a constant head is a constant flow or a constant, well, it's held with the head constant, whereas a river cell, it changes, or it can change. It can have a river condition, but the head in the cell can be different with that condition. It's a well-connected aquifer, and it's not, but we'll get into that. Then there's other things, drains that can only take water out. I could expect a drain to only take water out. And it's based on an elevation. And there's evapotranspiration. So we can say, you know, we have so much recharge going in, and then as the water table falls, a lot of that is evaporating out. This is the biggest thing we ignore, probably. One of the biggest things we ignore, because we lose a lot of water from evaporation. So how many of you have gone outside and tried to, well, if you don't have houses, but water your lawn and it's all cracked, right? You see all those giant cracks. Well, what's happening? You're getting water evaporating, and, you know, down to a certain depth, you can get a large mass of water evaporate from the soil. And so before the groundwater has a chance to take it away, maybe not in Tampico, but maybe out here, you know, it's going to vary quite a bit. So, or if the water table gets close to the land surface, like you had there in Henry, you can start losing a lot of water through straight evaporation, or these giant trees out here. Someone said a willow tree can suck up, what, 100 gallons a day or something, or 500 gallons a day. These trees use a tremendous amount of water, which is why they die when they run out of water. Different matrix solvers, we'll talk about that. And then different things we can add to the model, contaminant transport, MT3D, RT3D, optimization codes, calibration codes, all sorts of pre and post, or I guess they're all post-processing codes, but they take your MODFLOW model and do something else with it. I think, oh, this is out of Mary Anderson's textbook. So Mary Anderson up and Bill Wisner wrote a textbook on groundwater modeling. I'll put my copy in the war room if you want to read it. But this is kind of the modeling process, and you've probably all been through this in some form or another of the scientific kind of process, and it's pretty similar here. you know, what's the purpose of your model? That's the most important question. You know, what am I trying to do? Can I bastardize this old model to fit this new purpose? You know, it's a common question. This is where we run into our biggest problem, is a conceptual model. What is going on? We can't see groundwater. We can't see the geology. We can't see if the wells are in multiple aquifers unless we look through the data and all that kind of stuff. So, you know, you have to be flexible to change your conceptual model. You have to admit that you were wrong. It's like, oh, this isn't what's going on, or my preconceived notion, or, you know, whatever first thought was way off. They don't recommend. There's some other guys I would say are always way off and start reevaluating the conceptual models. But you know, it's field data and you know, with our transducers and other things, where we can put a 10x on this field data, the amount of new field data going in. With our geology that Jason has done, Jason Thomason, and now Dan's working on, you know, it's given us a tremendous amount of stuff that we didn't have before, tremendous amount of detail. And, you know, that's going to change our conceptual model drastically. Then we choose our mathematical model. And so go into this whole box on code. And really, this is all kind of stuff you don't need to worry about anymore. But on, well, unless Daniel's writing code, so I take that back. You know, how are you going to solve those equations? And so, you know, you got to write your numerical formulation, which is what MODFLOW is. You know, so these pre-existing models have been verified. You know, MODFLOW has gone through the court numerous times. You know, and that it says, it does what it says it does. You know, and that's really what you want. But if you're writing new code, say you're putting transducer data on a website and you see you're spiking up instead of spiking down, you know, then you know your code.
That's a data problem.
Oh, sorry,
Totally
I didn't mean to pick on you. You know, then you know there's a problem with the code, and you know, or something is feeding into the code. Sorry, not the code.
All my other wells look fine. It's just your wells that don't look good.
Yeah, mine are all upside down. What a surprise.
You know, I'd point out on that is that there's so many new codes coming out. So the old version of MODFLOW is well vetted, but MODFLOW 6, new, almost I'd call it beta still.
Yeah.
Unstructured grid was published before it was ready for prime time. Took 2 years before it made any sense.
Yeah, those first versions
even
were
the
horrible.
Tutorial examples were nonsensical. So they bring in a lot of things that are very attractive to modeling. Like George was talking about, piecing together models. What the Dutch put together, their own little homebrew version of MODFLOW, is, again, how well vetted are these new codes versus MODFLOW 2005, which is that same underlying structure. Everything since then are bells and whistles, and they're bells and whistles that have sometimes been lauded, but sometimes cause issues.
Yeah, it's not like Google, you know.
Yeah.
Google says they have algorithms, but they're so complicated that no one person understands them. So, you know, what's, you know, search on Trump and you get all these negative value articles versus, you know, something else. And, you know, is that a reflection of the data, or is that a reflection of some hacker somewhere that's changed the code? You know, this is a big topic that I was heard about. But, you know, is that every part of the code correct? Because, you know, somebody wrote a code that was thinking, it's an exaggeration, but, you know, I'm doing the rivers, and, you know, as long as you assume that all the rivers flowed south, it worked great. But wait a second, okay, this works for this river and this river and this river, so it must work for all of them. wait a second, this one that's going the other way is, you
I
know,
still don't know what you're talking about that I did there.
yeah,
I haven't
well,
quite figured
you
that
put
out.
it out of your mind, but
Yeah.
yeah.
And then another thing is understanding what's in these codes, because we've seen an issue where we'll talk about dry cells and kicking out pumpage in dry cells. And standard mod flow would tell you how much. And if you look at some of the new codes, they're doing some advanced things. And if you look, it says hasn't kicked any pumpage out when you look at the standard way. But when you dig deeper, it's kicked out almost as much pumpage as the original version. It's just reported in a much different way. So understanding how it's reported, because the report that we were reviewing said there was no dry well flow loss. At the moment, there was a lot of flow loss. So
Yeah. So remind me to put that copy of Anderson and Wisner's textbook in there.
yeah, and we should get a copy of the new version too.
Yeah, I have a new version. Don't you?
Yeah,
Or it's Anderson and Lang now or something.
a hunt is on it too.
Oh.
Yeah.
Well, that's a surprise.
Sorry, I interrupted with the coach selection part. You were at the model
Oh, okay. Yeah, so what code you're gonna use, Plasm, ModFlow, something else. Nowadays, we'd probably be viewing, like what Daniel said, we'd be using ModFlow, but would we be using on a structured grid or some other code that hasn't been as well vetted, you know, so is the code verified? Who verified it? And maybe we verify it ourselves. And Daniel's done a lot of that, like the CLN package. I think you were kind of wanting to see before we put it into the big model. Let's put it into a simple model and see what it does.
Yeah, can you replicate something that you know from a simple solution what it should be, and make sure that it gives you that. Sometimes it does, and sometimes it'll surprise you at how off it can.
Well, and a lot of these codes will have a whole bunch of different parameters.
Mhm.
You know, there's always an alpha and a beta somewhere. Transfer codes are really bad for this sort of stuff. You know, and what do these different parameters do? And if you have a big model, if you're throwing it into, you know, the Joliet model or something, and you don't necessarily see what it actually does because there's too many other complications. And, but if you do it standalone, let's see what the time variable material does and how these different parameters work in a simple 1D 3-layer or you know, simple 3D model. Then this is what this does, or this is what that does. Because you know, this is fairly well documented, I would say. I would call it pretty well documented. All the newer stuff is not documented.
Not documented at all.
I mean, yeah, it's really not documented. I wouldn't even go far to say it's even slightly documented. But
Yeah.
so a lot of those parameters, you may be looking at a users group where other people have guessed what they're doing, but don't actually know. And you know, the person who wrote the code might have put it in to get something to work, and so it may work in the test case, but not work because a lot of times when these codes are written, they're done in a specific test case, but people don't realize how they've geared their programming towards that specific test case in order to make that test case work.
And another thing to beware is that it's not just the standard, there's the ModFlow codes that you can go to USGS and download. And then there's the ModFlow codes that Jim Rumbaugh with Groundwater Vistas, which we'll be talking about, that he develops, and he'll make all kinds of tweaks, all kinds of little additions just to do that, just because he's a consultant. So he may be trying to get a model in Texas to work. And so he feels like he needs to add this or that. And it may just be for him, but it's in that logic. And good luck finding the documentation on what that does. We ran into that with the package that we're actually using as proprietary, though. We want to really avoid.
What was the package you put the -51 into?
Oh gosh, that was SFR. That was That wasn't a Jim thing. That was actually a USGS thing to get flow reported out for each cell. That may have been a Jim thing. Actually, I take it back. I think that was a Jim thing.
So you have to understand that these are written by small groups of people.
Mhm.
So it's not Microsoft writing Excel, and having an army of people do different things to make it all work. I mean, the MODFLOW group at the USGS is Chris Langevin, Joe Hughes, and 1 or 2 other people.
Yeah.
I know them and can name them. They're humans too. I mean, they're good at what they do, but and they have different priorities, and they know that there's problems with this and problems with that, but they're going in many different directions, so they don't have time to address them. And then there's consultants. And, there's one guy named Sorhab Pandey, who writes a lot of code, but how do we know he's writing it right? Still, or if he's writing it to solve particular problems that he has, because unstructured grid problem to address something in a nuclear waste repository in Washington might be a lot different than what we're trying to use it for in Illinois. So so now I guess in code selection, I went through this, passed by this box too quickly.
No, that's fine.
We know we're going to use MODFLOW under the hood.
Yeah.
But it's all the other packages, the solvers and other things that
We're going to be enticed to use the new versions because they have the bells and whistles. But I think verifying it, like George said, building a simple model, making sure it passes muster, that it's doing what you want it to do, is really important, because you don't have that, and the book, and you don't have years of experience that's gonna work like you want it to.
Yeah. I mean, we could just use this version, I guess, but we run it all.
You could, and then you start running your drive cells. That's a lecture in and of itself.
I mean, when this came out, the model grids probably weren't bigger than 50 by 50 by 3 or 4. And, and then it's all the post-processing. Okay, I got this matrix of head values. What do I do with it? I have to bring into something to see it, and yada, yada, yada. So the GUIs do all that stuff for you, and they make running a big, complicated model much, 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 much easier. So there's always kind of been a rule of thumb that we've kind of violated lately, but models tend to be as big as something that can be run in 4 hours. It's about the limit of people's patience. Daniel's a lot more patient, so our model takes a lot longer.
I think it can be run in 4 hours.
So
just haven't had the effort.
We're going to spend a lot of time talking about how to speed up a model.
Yeah.
Because it like the Muhammad model and the Kane model, I spent a lot of time speeding it up, because once you speed it up a model, the Muhammad model runs in 20 minutes. So the early versions, took hours, and so once it gets down to a reasonable time, then you can do a lot more with it. And you can modify it and stuff, and because you'll be modifying these models all the time and changing parameters and all that kind of stuff, but you want it to run pretty quickly. So discretizing the model, that's creating your grid, deciding where your grid nodes are, what your grid spacing is going to be, both horizontal and vertical. So do you go out, to, like in the Green River lowlands, you just model the lowlands itself, or are we going to extend the model out, up the Paw Paw Valley and maybe up the rock a little bit to get that complexity, or do some thinking about what's going on up there. We have to go to the discharge locations. We have to bring that model all the way down the Illinois River, get that discharge and wherever to the west. So, it's deciding where to go with your boundary conditions. So we think the Rock River and the in the Green River lowlands. This is kind of the north end of the flow system, but there's sand north of the Rock River. So, you know, are you going to model all the way up to the end of the sand or just to the Rock River? You know, as soon as you cut it off at the Rock River, something's going to go in on the north side of the river, and they're going to ask you, well, what happened? So my advice would be to go all the way to the edge of the sand. But, you know.
Great example, we cut our sandstone model off at the Mississippi River.
Yeah.
And we need to model Iowa. So fun stuff, needing to expand the model. That's a lot more of a pain than having done it in the first place to capture what we actually needed.
Yeah, as much as we want to pretend Iowa doesn't exist.
I know, it exists.
It exists.
It exists, like it or not.
Not in this room, it doesn't.
Yeah. And of course, how you define it vertically, you know, in days gone by, we used to use much more even layers. We didn't have a way of displaying variable grids. And so they still don't do it well now. I guess Vistas does it fine. The visual model, like, you know, the bottom of the aquifer is uneven. So it used to be when you plotted it up, it would make the bottom even and distort everything from there. So they put in a dummy layer with a flat bottom just to get it to display right in the GUI.
That's why you guys did that.
Yeah.
Okay, I never understood that.
Why there's a completely
Why there's a no flow layer at the very bottom.
It's all fairly
Oh.
graphical.
Okay.
So yeah, I'll point that out in ModFlow model. Yeah, because the early versions of this didn't do that right either.
Gotcha.
This makes the whole graphics a lot easier because then you can, instead of just having this nebulous white bottom, you can actually color it and say,
Yeah.
okay, that's the bedrock. And, you know, so these sands are pinching in and out. So the way you might do it with an even grid is, you know, the sand is twice as thick here is over there, but you know, you change the transmissivity. There's a basically changing the K through here to reflect changes in thickness. That gets really complicated. You know, as we've gone on, we've definitely gone to something more like this, where the layers change with thickness. So old ModFlow, original ModFlow, good, reliable, verified ModFlow, requires a layered, if this is our geology and we have, you know, the sand or this clay layer, say the yellow is the sand, and it pinches out. You know, it doesn't exist over here, so we just have one aquifer, say our Tampico and our San Cody. In regular ModFlow, that layer needs to exist through the whole model. So, you know, so you got to decide how many layers you have or how many you really need. And even if a layer only exists in one area, again, it needs to go throughout the whole model because it's a grid and it's looking for, that operator is looking for the next grid cell over in that layer to solve the head equation with. And if it doesn't find anything, then it just crashes. So ModFlow requires grids over the whole area. And I was saying bottom layer being variable, this is like in the Muhammad model, this is all the no flow layer just to make the graphics good. But so newer programs, unstructured grid we'll talk about, doesn't require this. The layer can just end right here, and then there's some funky math that goes on here to make one cell match up to two cells, or vice, yeah, one. And so it uses these ghost nodes and stuff, and I guess we'll have to, it might be worthwhile for you to explain that just so you understand it.
Yeah,
I'm not convinced.
actually,
I
the math
understand.
behind it, I'm happy to do that.
Okay.
Not now, but I will look through the math of it.
Because, yeah, so,
Yeah. But that's where GUIs help in terms of setting up, because there's a lot of setup that has to happen to make this work right.
yeah, so, yeah. Yeah. So if I have one cell up here going to 2 cells, you know, and then maybe even farther down, we go to 4 cells. So the MODFLOW is looking to calculate a flow budget, you know, across all these different interfaces. But this cell is bridging 2 cells. So the flow that's coming this way has to be divided either in 2 or in some sort of fraction to serve each of these cells. And it's an approximation. So you have this approximation going on, not an exact solution.
Yeah.
Where,
So the way it resolves that with ghost nodes is it will mirror that node in that bottom cell, and yeah, right across there it will create some additional nodes, and then that flow budget, it's approximating, as George says, how to spread that out. The rule of thumb is that you should only ever go 1 to 2. You shouldn't have 1 to 4 down there. So the way George did this is correct, where it's going 1 to 2, and then each of those go 1 to 2.
Yeah. The ghost nodes decompose the larger cell into 2 cells and then it flow across the boundary.
Yeah.
Rather than 3. Okay.
say we have the Illinois River here, and it's a sandstone outcrop, right? So it's a St. Peter sandstone, and as you go to Chicago, the St. Peter, it's heavily buried. And we have all these other units here, and then all our glacial units in here as well. So the St. Peter might be down in layer 13, but here it's at the surface. So for regular MODFLOW, we have to thinly drape or do something, all these layers over here. So when we get down to here, there's all these extra layers that it has to calculate. So we can make them inactive, which gets really messy. We can make them all within the upper, 10 feet or so, and you can give them 1 foot thickness, or
and then they're likely to go dry.
they're likely to go dry and
Which
cause
is-
all kinds of problems. So another thing we can do, is kind of drape them all underneath, and so if the St. Peter was, 100 feet thick, but we have 13 layers, we might have, a 10-foot layer, then a bunch of 1 foot thick layers, all given the hydraulic connectivity of the St. Peter, but then our St. Peter cell itself might only be, 80 feet thick. So, we can't create or destroy geology there, but you got to have all these layers. So if we go to unstructured grid and we're able to take these 13 layers out, that removes millions of nodes from the problem, and it's going to make it solve a lot faster.
It's an enormous gain.
Yeah, it's an enormous gain because a lot of these fill layers don't exist everywhere. A lot of these bedrock layers don't exist everywhere. So if you can lose those millions and millions of cells instead of having all these 1 foot thick cells. Now the 1 foot thick cells that are the same permeability as things above and below solve really fast. What slows the solver down is permeability contrast.
And the pre-processing, the most challenging part of the year-long process of developing the new Illinois model that George talked about, the most challenging part was the pre-processing of all these layers where they pinch out, making sure that that geology is reflected properly. is actually rather disappointing after spending all that time when I was able to just pinch them all out at the end. Like, okay, well, that was effort that I didn't even need to go through at the end of the day.
So, yeah. So this is kind of a new frontier of modeling that we're going down. So, I mean, if you look at our past models, it won't have anything about this in there at all. You know? So it's allowing us, hopefully, to go forward much better than we did in the past.
But it also creates some challenges when you start looking at flow budgets and some wonkiness with flow budgets through pinched out cells. So when we get back to vetting the code, it limits us some in what we do with flow budget, at least right now. You have to be very creative on it, and you get some pretty bad flow budgets if you're not careful.
And if you get a bad flow budget, then you got to worry about, is this model telling us anything, or is it just garbage?
No. Nope.
You know, the nice thing about a simple model, just using the basics, is there's none of that voodoo going on you have to worry about.
Mm-hmm.
I say voodoo, that's just because I don't understand it.
There's math behind it.
There's
but
math behind it.
Yeah.
You know, but this math's really correct. You know,
Or
I mean, it might be
something.
correct in theory, but is it really applicable to what?
We should spend a session talking about dry cells, and I'll try to explain what in the heck Newt does.
Good luck
Because
with-
that's the
good luck with
basis
that.
for all of this, something called Newton-Raphson and upstream weighting. It's this big shift in MODFLOW that a lot of modelers say is great, but it's because it speeds their model up and allows them to take some shortcuts. So we should talk about the math behind that at some point.
So it's already afternoon, so I'm just going to finish a few slides on gridding and then save the rest for later. So this is a way we used to do it, variable space grid. This is your area of interest, but you want to get out. You know, your boundary conditions are out at distance. So you need those boundary conditions, such as the Wisconsin River. This is Madison. And so this is done to save computational time. So if you had all these cells down here, your solver is having to run through, 100 extra cells down here that is an area that, it's not your area of interest, so it's just going to slow everything down. But as we move in the Illinois groundwater flow model, we have areas here, here, and here. So basically the whole state's our area of interest now, much more so than that. But that doesn't mean we can't take the Illinois groundwater flow model and telescope it back down to something. And we'll talk about telescoping a little bit. This is an example of telescoping where you have a big regional model and maybe a more local county scale model, and then you can zoom in and go even further. So this might be, for example, our Kane County model, but we wanted to model a quarry in Crystal Lake, Illinois. And so we zoomed it down to a specific location. So we'll do some telescoping models. So these are finite difference models, and then there's finite element models. So finite difference model, you can think of as squares or rectangles or cubes. You don't have to be constrained by that quadrilateral geometry. You can use triangles or other odd shapes. So this is one using triangular elements. So each cell is matched with another cell face, so you can directly calculate, from one cell to the next. And you see these where you have big changes in scale. A lot of, in this case, it's a dam. The dams always fail right here, right underneath. So you need a lot of detail right underneath, but you can't ignore the whole flow system. And so the geometry is also such that if you just had horizontal layers, you get really odd pinching of flow and very poor representation of the flow, around this structure. So you can't use a regular rectangular grid. Here's another one. We have a river, an Italian river, flowing east. You know, and there's some kind of weir here, and a wall, and some kind of control structure. So, you know, it's most likely to fail right at the edge, or, you know, right underneath. So they got a lot of detail there, but they also need, hey, what's going on, the regional flow towards that. This is something where we're just touching on unstructured grids. This is called quad tree refinement, where you see one cell going into two, and then that cell going into two more, and so on and so forth. And so this is allowing for a finer resolution of your river system, you know, and then away from the rivers, where things aren't changing as much, you may not need as much detail. So Daniel Feinstein in Wisconsin, did he use quad tree for layer one?
Yeah.
And then standard grids.
I think he actually just went with a uniform, really fine mesh in layer one.
Oh, okay.
But I think he's used quad tree in another model.
So, you know, is this something we need to consider for our rivers? Just throwing it out there. Oh. Then there's something called Veroni cells, that where, I don't even know how to explain Veroni cells, but math gets a lot more complicated.
Yeah.
But you have
Ghost nodes are going crazy in this one.
go through the crazy, yeah. So you have all these different shapes. You can, you know, any kind of shape you want, as long as you have the math behind it, I guess, to back it all up. So here, for example, you have 4 nodes going into one. You know, but it's, I don't know how much this is catching on at all, but
I don't know. Jim
Jim
allows you to do this in Groundwater Vista 7.
Yeah, I haven't really seen anybody using it.
I haven't either.
But
I see a lot of quad tree though.
I think it's being used in other kinds of, in other branches of engineering for some modeling. I know some of the structure people use this kind of stuff
Yeah.
for like I-beams and things like that.
It's just hard for MODFLOW modelers to get away from the grid.
Yeah, my son uses a lot of finite element modeling for like failure of railroad ties and railroad rails, you know, because the stresses are not evenly put on the tie. And then we'll stop there and pick up. This is a call, but I need to go over to Carl. My dad's or father-in-law's having heart surgery, so yeah, then we'll continue on. So I kind of went over some of the basics a little bit, but I think this will get much more discussion oriented. One day I watch in the room, it gets much more discussion oriented.
Sorry.
No. Because yeah, I mean, a lot of what I want to accomplish here is kind of tell you where we've come from, but also where we need to go, and you know what I can just leave and then pretend that all my models are super and that they don't have any flaws and all that kind of stuff. But you know,
Well, we also don't want to look at him and be like, "What was he doing here?"
what was he doing there? Yeah. Why is there?
Okay, I don't understand it.
Why is there an inactive layer 8 under everything?
Yeah. Yeah, and I think also what you touched on in terms of speeding up models. I think that I've always viewed that as something that is a very strict sort of procedure that you followed.
Yeah.
You look for this, then you do this. You
Yeah.
look for this, then you do this. That's something that, in theory, I think we can code to a point. And then evaluate how that's working and go back in and do some manual changes. But I think that there's ways that we can let that run in the background and help improve our models. Just in the background while we're doing other things.
Yeah, and I think it's fair to say, you know, when I did some of my modeling work and others before me, that one person could kind of do it all. or a lot of it, but we've gotten beyond that. It takes a group effort now. And a lot of people are looking at it in different ways to kind of, if you want to get beyond the simple models, well, simple models are done. Check the box, move on.
Yeah.
Or, we want to get somewhere, we got to get a lot more complicated, a lot more detail in, especially as we get more transducer data and other data.
As we get more transducer data and start doing more transport.
More transport,
transport
more questions about flooding, more questions about East St. Louis going to pot, and because you can already guess that the standard model, steady state model is not going to work for East St. Louis.
Yeah.
Handle flooding. It's not. So
George, I think I told you October 14th through 24th, we're trying to get Kevin to approve funding for a transport webinar series from Jim,
yeah.
where he'll run through basic transport concepts. We'll expand on those here. He only has 2 hours to do it. And then on top of that, talk about MT3D, and then some of the new beta, let's just call them unvetted transport packages that we may want to use. But again, we have to make sure that we trust them.
Yeah.
So I think that just kind of is something that we want to get an early start on. So that'll be October 14th to 24th if we get funding for it. I don't think that's going to be an issue one way or the other. But I will fill you in on all the details of that. I'll give you the information if you'd like to join in there as well.
All right.
Okay.
What do I need to do here?
Yeah, so this is gonna help with that. Just open this back up.
Oh,
and
save
then
all my transcripts.
stop